on track. All right, so here we go with Unit 17, the final unit of pre-cal, 3 days of notes, and that is it, and we're almost done. So, if you're at home, print this thing out. We're going to work through it, not necessarily in order. We kind of jump around a little bit. So pay attention closely. And actually, you know what? I have the plan for what I'm going to do. I'll post this as well so you can follow along ahead of time on jumping around here. All right, historical note. Read it if you want.
I don't want to sharpen the pencil on you.
Go sharpen your pencil. It's fine.
I don't have.
You're interrupting
Now you're interrupting.
Yeah, now you're interrupting the video.
I'm sorry,
Andrew. Now I'll call you out on video.
Andrew,
All right, well, let's back up a second.
You kind of ate that pencil though. Good sharp.
So we've done a little bit with polar. Polar is r and theta rather than x and y. And what we've done so far is graph points. That was on the last real test we had, which feels like 3 months ago, even though it was only, 2 or 3 weeks ago. It's just been a while. So we're a little bit familiar with polar, using r and theta to describe a point rather than x and y. And just like x and y, it kind of led to y equals some function of x. And so we learned how to graph y equals x squared, or y equals mx plus b, or all those other graphs that we learned in rectangular form. Well, this week we're going to graph r as a function of theta. And this is completely new, so you're not going to get there immediately. But we hope to get to the point where, you recognize, I think everyone knows what y equals x squared. What shape is that? Yeah, some of you are drawing or saying it's parabola. What about y equals mx plus b? It's a line. So you know those because you just recognize their form. We're going to get to the point where you recognize things like that. Now, right now you have no idea what that looks like, and that's fine. I don't expect you to. But by the end of this week, you'll need to know what that is. Or maybe there's an in there. What does that do? Well, we don't know yet, but that's what we're going to learn. So just like there's sort of a set of parent functions in rectangular that you're pretty familiar with, and you have an idea what their shapes look like without having to graph them, without going point by point, you know what those look like. We're going to get to the point, at least with notes available to you, where you could look at those equations and think, oh, I know what that's roughly going to look like. And then you'd fill in some details to get the exact graph, just like you would here. You'd have to know a little bit more to find the parabola or the line, but you got the basic idea. So that's what today is, to get to the point where you know, or at least recognize with notes, what some of the parent functions are in polar. In fact, it says, in this section we will investigate the classic polar relations. In fact, you could almost think of that as the parent functions in polar, such as the polar roses, cardioids, limnoscates, and circles. Now, you may not even know what the heck those words mean right now. You know what a circle is. Other than that, you don't know what those words are. But that's the point of what we're doing this week. All right, so part one. One way to graph these is to graph in polar what we know how to graph in x and y. In fact, this was the roller coaster project, was graphing things like this in x and y. So we're going to graph it in x and y and then figure out how we can translate an xy graph into a polar graph. So this was part of the reason, not just the fun and great reason for the roller coaster project, but the actual educational reason for the roller coaster project was to remind us how to graph these things. All right, so if x is 0, cosine of 0 is 1, and 2 plus 3 is 5. Or, you know what, maybe even easier. Instead of instead of going point by point, we know what that graph looks like. We know what cosine looks like. All of you described what A, B, and C do. So this graph is up 2, has an amplitude of 3. So maybe we could graph it that way. There's an up 2. Amplitude of 3. And cosine starts at a maximum. So there's our 0, 5 point. So again, you can graph it with the points, or you can graph it because you know what this graph looks like. At 2 pi, it starts over. Halfway in between, it's at a minimum. This is kind of jumping back and forth, but let's check one in the table here. If I plug in pi over 2, 2 plus 3 cosine pi over 2. Well, the cosine of pi over 2 is 0. So at pi over 2, I'm up at 2, which is what we would expect based on what we know about how that graph should look. At pi, 2 plus 3 cosine pi. Cosine of pi is negative 1. So 2 minus 3 is negative 1, which is what we thought would happen. So we know what the cosine graph looks like. In fact, that's probably what the first piece of your roller coaster looked like, was that first half to go from, on the roller coaster, 0, 10 down to 4, 2. So that should be reviewed. That we know how to do. Now we want to plot these values on a polar graph. And it may be helpful to create a table of values. So let's do that for this one. Theta and R. Where it even helps us here. Theta is analogous to X. R is analogous to Y. So we can use those same points we used. So if theta is 0, R is 5. If theta is pi over 2, R is 2. It put the 0 on there, but you'd have to really do some work to figure out where that is, so we're not going to worry about that one. At pi, we were at negative 1. Oops, I guess we should finish the table. 2 plus 3 cosine 3 pi over 2. Let's see, cosine of 3 pi over 2 is 0. 2 plus 0 is 2. Oh, I guess I could have just gotten that from the graph as well. And then at 2 pi, I don't have to plug it back in because I know it repeats every 2 pi, so it should be right back at 5. So let's plot these points and see if we can figure out what's going on. So theta 0, R is 5. 1, 2, 3, 4, 5. So there's point A. Point B, pi over 2, comma 2. So rotate to pi over 2. And go up 2. Now here's kind of the tricky part when it comes to graphing these. I'm not just going to connect those with like a straight line. As theta increases, so as my angle gets bigger, the R gets smaller. So as I rotate around, my R gets smaller. So I'm going to see if I can do this. I'm going to start here. I'm not just going to connect the dots. I'm going to rotate and gradually get smaller as I get there. My R gradually gets smaller. Point C, we rotate around to pi, and then we go negative 1. So point C is actually back on this side, But we didn't get there a positive way. We rotated around the pi and then backed up one. So that means, especially if we look at this graph, r continues to get smaller and even goes into the negative. So it's smaller, 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 and then it goes negative. So the graph goes through the pole and kind of loops back up towards C. It's not a spiral. It looks like a spiral now, and we will do a spiral later. But this one's not a spiral, because let's keep going and see what happens. If we rotate 3 pi over 2, so all the way around, and then go out 2, puts us right there. So we're continuing to rotate. So we rotated all the way around here. So it's kind of a loop-de-loop thing going on. And then I'm almost out of colors. But point E would be right back to point A because we've gone all the way around. It looks a little bit like a heart. It has that loop in it, and so you're really close to guessing which one this is if you look at those names, the weird names up there. You know what cardio means in heart, but a cardioid, this one doesn't look quite like a heart. This one's called a limaçon. Another French name there. Not a limacon. Like a bean. It's not a lima bean. It's a limaçon. And it has a loop, because there are limaçons without a loop. Alright, we did that one really slow. Don't expect you to have that memorized or anything. We're just trying to get the feel for how this works. But that's one picture that we get from doing the graph that we know how to do, the y equals x graph, and then sort of translating that into an r theta graph. All right, number 2. Or excuse me, we skipped. Oh, that was kind of one problem together. Number 3. Next page. Kind of the same type thing here. So let's graph 3 plus 2 sine theta. I'm going to rewrite that to how we generally like it. So that means our vertical shift is up 3. Has an amplitude of 2, but let's be careful because the sine wave starts at 0. So we'll start at 0, not really at 0, but on the axis. 2 pi later, we're back there. So we're mapping this picture onto this picture. Halfway in between, we're at a 0. Half of that, we're at a max, which a max is 2 up. And at 3 pi over 2, we're at 2 down. Now let's take each of those points and sort of translate them to the r theta graph. So that first point is, let's see, r is 3 and theta is 0. 1, 2, 3. So there's point A. Point B was 5 up, and pi over 2 is the angle. So we'll rotate to pi over 2 and go out 5. Do you want to plot all the points first, or do you want to play connect the dots as we go? Connect first? Okay, I think that's probably wise until we get the hang of this. Otherwise, you get overlapping points and you're kind of not sure where to go. So we got to get from A to B, a smooth line. We're not just drawing lines. We're going to kind of curve our way out there. All right, point C, the angle is pi, the radius is 3. So we'll rotate around to pi and go out 1, 2, 3. And kind of the same thing. We're going to keep rotating from B to C. Let's see. Point D has a radius of 1 and an angle of 3 pi over 2. So we rotate to 3 pi over 2 and go out 1. And then that last point, we rotated 2 pi, and the radius is 3. So yeah, we're right back to A. So here's the deal. For it to be a cardioid, it has to go exactly back to the pole. So yes, it looks like a heart, but it's not a heart, at least officially, unless it goes exactly back to the pole. So the pole is the origin. So this is another limaçon, but no loop. All right, number 4. What does that 2 theta do? What does the 2 in there do? Roller coaster experts. Yes, changes the period. So this period is going to be pi. So let's see what happens. So I want to graph sine, but it finishes at pi. And we have a amplitude of 2. We're kind of missing this doesn't fall on the grid line exactly here. So there's my graph from 0 to pi. But I need to graph it to 2 pi because on my r theta graph, I got to go all the way around to 2 pi. So I need to go ahead and extend this to get it to 2 pi. Now, once you've graphed it once, hopefully extending it isn't really that hard. All right, so 0, 0 is a point. Starts at the origin or the pole. And then this point is 2 comma pi over 4. And it's curved. Okay, also 2 pi over 4, that's the maximum it gets to. So that's the farthest out. The radius measures how far out we go. So that's as far out as we go. When we're back to pi over 2, we're back at 0. So we're going to sort of curve our way out to 2 and then curve our way back to 0. Should have switched colors here. All right, let's see, that would be 3 pi over 4. We're at negative 2. So 3 pi over 4, but negative 2. And then at pi, we're back to 0. So we're going to loop out to 2 and come on back. I feel like Andrew's right. It is going to be a flower.
Yes.
at 5 pi over 4, at 5 pi over 4, we'll loop out to 2. Let's see, how does... And then, let's see, what color's left? Blue. And then, you probably don't even have to go point by point on that last one. What quadrant is the last petal going to be in? The third. It's got to be. It's the only way it makes sense. You know what? Shit, I did that wrong. Still looks right, but I put those in the wrong quadrant. So that's a rose. I don't know if you like it as a rose or not, but that's the only flower name we like. So that's anything that looks like a flower is a rose. Right? Math students generally aren't artsy enough to come up with a better name for a flower than just rose. So, does it look like a rose? Not really, but that's what we're going to call it. All right, last one. Pi equals 2 pi, theta equals 2 pi over 3. All right, this one's, so theta, so this axis is like theta, and this axis is r. The second mark is pi over 3, because it's going by pi over 6s. And so I want all the points that are at pi over 3. It doesn't matter what r is. So do you know what this graph is going to look like? No. All the points where theta is pi over 3 and it doesn't matter what r is.
Oh, okay. It's going to be a circle. No.
When I come over to this point, when I come over to this graph, let's see, pi over 3 would be right there. I want all the points on pi over 3, and it doesn't matter what r is. So it doesn't matter what r is. I want all the points on pi over 3. But also, if r is negative, it goes back the other way. So it's a line. All right, here's what your homework for today is. So turn a couple pages over to where it says graphing polar equations. You can omit 1 and 2. Omit. So the page that looks like graphing polar equations at the top, with the on-ramps logo thing at the top. We do not omit the whole packet. So turn it over, look at number 3. So Monday's homework is 3 through 6 on this page. So 3, 4, 5 on that page. And you're doing exactly what we just did. You're going to plot the graph like we normally plot the graph, and then see if you can translate it onto the polar graph for 3 through 6. So we'll stop at 6 for today. And then one more on worksheet 2. On worksheet 2, yeah, we don't want to do that one yet, but we could. Worksheet 2, do number 3.
Okay. Yes, sir.
So on worksheet 1, you're doing 3 through 6, and on worksheet 2, you're doing number 3. 3, 4, 5, 6, and number 3. So 5 questions. jumping around a little bit, but 5 questions. 3 is laid out a little bit differently, but it just gives you a very exhaustive table of values, and then plot them as you go and see what happens for 2 plus 6 sine theta. So give those a try. We'll do some tomorrow, and we'll just kind of keep working through these strange looking graphs.
Number 5 that we just did, why did we graph it as pi over 3 when it's 2 pi over 3?
Uh-oh, did I mess that up?
Well, it said theta equals 2 pi over 3 and we drew the line at pi.
Yep. So thank you for catching that before I stopped recording. Number 5 on the examples that we did. Good catch. You see the problem?
I do.
I graph theta equals pi over 3.
Let's change the question.
That's
Well, let's just graph another one. So that's the line theta equals pi over 3. If we want to graph what we were supposed to graph, we'd go to 2 pi over 3. And we'd graph that line. So we did 2 examples instead of 1. That was the plan all along. Good job on catching that. We did 2 lines instead of 1 because we're strivers like that. All right, so please try those because these get tricky. Like this is the first time you've seen this kind of stuff. So try them. We'll go over them tomorrow and we'll just keep practicing this weird polar graphing thing.